So let's we do this tutorial one together. Okay, but you have to try first and uh, post in the Padlet so that we can discuss together. You can discuss with your friends also. Consider an alloy containing 70 weight percent of nickel and 30 weight percent of copper. Okay, see figure. Actually, the figure is in the next slide. Okay, at 1350 degrees C. Make a phase analysis assuming equilibrium condition in the analysis including the following. What phase are present? This one is A1. Okay. A2, what is the chemical composition? And AC is what the amount of each phase is present. Okay. And B, make a similar phase analysis at 1500 degrees C, as well as C, sketch the microstructure of the alloy at each of these temperature by using circular microscopy field. So how you going to solve this problem actually? Okay, so this is the figure. Okay, if you can see this figure, right? Okay, I just make copy this one and then make this one small. Okay, and paste here and to reduce. Okay, so can you do this one? Okay, let's try first. What the face are present? What are the faces are present? Okay, can you see here? What face that you can see? So initially, if you have this one, okay, the starting W naught is 70%, so it's around here. Okay, this is the 70%. This is the line. Of this one. Here it said it's a 1350, so I think it's around here. Okay, what do you think? Okay, so just see the cross line. Okay, what are faces present? So please write in A4 paper. Okay, are you done? And what is the chemical composition? And what is the amount of each phases? Okay, so if you look at here, this is the W naught, right? This is a W naught. Okay, so similarly, how can we determine? Draw the straight line. Okay, this one is WL, and this one is WS. WS, yes. It touch the solid and liquid phase boundary. Okay, so if you look at here, what you do? Right, this one, and also this one. This one is WL, this one is WS. Okay, so what is the answer? Okay, for A2. Okay, and then what amount of each phase is present? Okay, so just refer to the equation, okay, or the formula in the previous slide, right? So what you have to do, okay, for XL is equal to what? WS minus W naught divided by WS minus WL. While for XS, for solid, right, equal to, okay, what is it? W naught minus oh, sorry, double click. Okay. Oh my god. This is the limitation of the WebEx. Once you double click, it disappear. So XS equal to W naught minus WL divided by WS minus WL. So you can get answer for the amount of each phase present for the solid as well as liquid. Okay, so that is the answer for A. Please write the answer. I want to know the answer, and then you can post in the Padlet. And also for B, okay, similar phase analysis at 1500. So how do you do this phase analysis? Okay, so what you have to do is at 1500, okay, look at here, right? Definitely you know the phase, okay. Just draw the horizontal line here, right? And then with the W naught is 70%. So you know already what is the phase, right? So you can see clearly. Okay, and the microstructure. Okay, sketch the microstructure of the alloy at each of this phase temperature by using circular microscopic field. Okay, so at 1500, what is the microstructure? This one. So that means just around the size is maybe around what is it? Size of the coin, 20 cents or what 10 cents. Okay, and 1350. So this is the what you have to draw. Okay, what is the microstructure? Okay, so you have to draw. You do like this. Oh my god. Okay, what is the microstructure development at 1500 degrees C as well as 1350? Can you draw? Yeah, I give you the link for the Padlet. Okay, this one. I'll give you about 5 minutes. I already give you the hint, right? So, see in the chat box the Padlet link. Okay, so I want to know the answer. Can you do? For the test or final, generally is gonna be like this, the question. Okay, you can see this diagram also if the similar diagram, but mostly on solid and vapor for the thermodynamic chemical engineering. Okay, chemical engineering thermodynamics. So you can see the similar figure, but for liquid and vapor, this one is liquid and solid. So for those who done, can post in the Padlet so that we can discuss. Hope you can see this one. For those who want directly draw by using this figure from my PowerPoint slide, you can just print screen and paste in the what is it? Any platform like a pen or drawing pad, something like that. So you can draw. Okay, you know, paste in the Excel also possible. Okay. Okay, you can just print screen, copy and paste. So I give you 5 minutes until 9:25.
Doctor, what is the difference between what is the chemical composition and what amount of each phase is present?
I don't know. Just kidding. What is the chemical composition? Just now I already explained. What is the chemical composition? What do you see in this figure? What is the material? What is the material that to make that this alloy?
Nickel and copper.
Okay. So how many percent is nickel and how many percent of copper at 1350? Okay. Is
Oh,
it clear?
okay.
Okay. So that means that for A2, this one chemical composition. So this one you determine, right? For example, this one you determine this one is a WWL. So how much is how many percent of nickel? Okay. Okay. For example, this one also. Oh, this is for starting is a W naught is 50%. Almost similar this one for diagram, but this one is for 70%. Right? So this one is WS. How many percent of the chemical composition of the nickel, and the rest is gonna be copper. Okay. Okay. This one is more to like how many percent is liquid, how many percent of solid, XL as well as X, XL, XS. Okay. Okay. Anyone done? Already post in the panel so that we can see maybe one or two. I just want to see whether you understand or not about this one. Actually, is I think it's quite easy. It's a straightforward of the topics and also some question. It's really straightforward. Okay. Still nobody post in the chat. Okay. So I give yeah, you have another 2 minutes. 2 or 3 minutes, something like that. Okay. So time's up. Can you pause? It doesn't matter if you finish or not. Anyone? Because you also gonna do the tutorial. It doesn't matter if you finish or not. Can you pause? Anyone? Nobody? So I just call one name. Hmm? Anissa? Fatina? Or maybe Ramadan? Can you post? It's okay if you're not finished. We're gonna discuss. Okay, Andy Zafran. Okay. Yeah, maybe Andy Zafran gonna share his answer. So just verbally maybe okay. There's one this one from who? Anonymous is okay. Maybe I just guess. Oh, so small. Uh, okay. For one is liquid and solid. Is this correct? So maybe it's good if you can because it represent L and alpha. So we can write as L plus alpha here bracket L plus alpha. Okay. So liquid and solid. Yes, that's mixture. So for the chemical composition, how many percent? So small, 59% of nickels and 70. Yeah, is correct. For me, it's correct because you. But for me, maybe because of the is not really accurate, but it's okay. Okay, is your answer. Okay, I think it's almost close. But for me, is 62%, almost close. So still correct of the nickel, and the rest is for the copper. Well, this one's I got is about 72%. Yeah, it's just based on your observation, right? So it doesn't matter. Sometimes you can see just around 59 or 60 is acceptable this answer. Okay. So for the liquid phase, how do you get? Oh, since you use 72%. Okay, I see. 74, 69. Is it W not is 69? Is it WL? The WL you got is 69. This one WS. This one is WS. And this one is WS. So this one WL is a 59, not 69, isn't it? Who sent this answer? It should
Oh
be
yeah, Doctor.
yeah 59. It should be 59. This one 59. Okay? Because this one you wrote here is 59, so it should be 59. So it's gonna be I think it's more reduced around half about 40 to 30%, isn't it? Okay, 40 to 30%. Uh, okay, 30%. Okay, just recalculate again. And then this one is yeah, it's correct. Just yeah, of course it's the wrong answer, but it's correct equations. Okay, it should be 59. And then it's about 60%, isn't it? But my answer is this one. If I'm using a 62%, my answer is a 33.3, and this one is 67. Okay, 67%. Okay, so that's the answer. So how about the microstructure for at 1500? Okay. So for me, if for me, how I did is definitely you can see just based on the observations. Okay. So if you look at here, since this one not answer, okay, I'll just share the answer. Okay. So if you look at here, definitely, if we draw horizontal and vertical at 60% of nickel, okay, it's gonna be 100% of liquid. Okay, 100% of liquid. Okay, that one is for B. A already answered, right? And then for C, For C, okay. Since yeah, this one, okay, 70%, and then 1,500, okay, as well as 1,1350. Okay, here. Okay, how do you sketch the microstructure? So if you look at here, okay, I just make an oval shape. Okay, just make an oval shape. This one also oval shape, and then one line. Okay, this one and as well as this one. So this is of course 100% of liquid at 1,500. Okay, this is 1,500 degree C. Okay, so just you write as a this one as a 100% liquid. Okay, okay. So for two-phase system, liquid and as well as alpha and alpha solid. Okay, what you have to draw is you draw something like this. Okay, is there is a some alpha solid, right? Okay, so this one is okay. This arrow is for the liquid phase of L. Liquid phase is L. Okay, and this arrow for the solid alpha phase. Right. Okay. So this is how you sketch the microstructure. How about this one? Okay. If this one's just refer for the previous slide, is going to be solid, solid, solid. 100% is solid. Okay. So you just draw something like this. Okay. Maybe you can, what is it? Make it like shade all this one to differentiate. Okay. Okay. Like this. This is 100%. If the temperature around 1,200. This is how you sketch the microstructure of the alloy. Okay, is it clear? Any question about this one? Okay, maybe today yeah, I think it's a straightforward question. Any questions from the phase diagram before we move to the phase eutectic? Any? Okay, so no question. Okay, I think it's clear. Maybe today we discuss just some part of the phase eutectic. Okay, just around 30 minutes. Okay, just 1 hour. Okay, because actually it's beyond our schedule. Okay, so let's we move. I think yeah, this one tutorial two, how to draw microstructure. Is there any reference how to draw? So if you want to draw, just like now, okay. So you similar like this one, okay. Is we don't have any size or any reference, just based on your imagination. Okay, how you to draw. For example, liquid is 100% liquid. There's a no particle or solid. So you just draw something like this. Just draw. Maybe the size of 20 cent coin, the coin of 20 cent or 10 cents. Okay, and then just imagine here. This one is start development of the solid. So just you make it dot, something like that, based on your imagination. And then it's gonna be what is it, grow, right, the solid. So just make it a little bit grow. Okay, you just draw generally it's gonna be uh the shape is gonna be circle, okay, or round shape. Okay, and then this is if during cooling, right? So the development of the solid. So and then after that, after you reduce the temperature, the solid is become bigger and they grow. And then this is 100% of solid. So just you make like this. Maybe you can differentiate if you use the pencils. You can differentiate by shading the what is it, the solid structure by using the pencil, right? Just shading something like this, the solid. Okay, if this is your round shape, okay, just make it shade. Okay, so differentiate between the liquid as well as solid. So if for solid, so you can do like this. Okay, you can do, okay, then you can just shade it. Okay, also possible. So is it clear? Is it clear, Andi Zafran? So just based on your imagination, okay. Of course, from liquid to solid, you can see the changes in the development of the microstructure, right? Okay. 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 So this is tutorial 2. So if you have times, you can do. Okay. And then let's see, we discuss on the phase eutectic. Just a brief discussion about the phase eutectic. So just want to tell you that is binary alloys. Many binary alloys system actually is they have a solid solubility limited solid solubility. Okay, so between, for example, like this one, right? Lead and stannums, copper and argons. This one, lead and stannum is for the solder. Candelabra is for copper and argentum. Uh, 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 and then actually similarly they have for the phase diagram is going to be separated by the phase boundary. Okay, so this is the example of the phase eutectic. Okay, so three single phase region, if you look at here. So here is alpha on top. This one on the left side is a solid phase. This one is liquid, blue one, L. Okay, so left side is the solid alpha. Okay, and then on the right side is the solid phase. Okay, for beta. Okay, so this is the boundary. And then generally for alpha, okay, uh, A reach a solid solution. That means for the for the compound A. So since you read here, so this is 100% of 100% of A, and this one 100% of the for B. Okay, so that means B is a solute, only small amount of B here. Okay, and then A as a host or parent. Okay, and beta is A solute because this one is the composition is reduced, right, from the left to the right for the A. Okay, so A is become solute and B as a host or parent. Okay, okay, so this one is a two-phase region. Okay, just remember this one alpha and L alpha and beta, right? This one. So of course, definitely on the right side, liquid and beta, and this one liquid and alpha. This one 100% of solid, alpha and beta. Okay. So this one 100% of liquid, 100% of alpha, almost 100%. Not really 100% because there's some solute uh, uh, B here. Okay. Similarly also for beta. Okay, and this one is for liquid and beta, liquid and alpha. Okay. So they have also two phase region, but this one not 100% solubility. So you have to remember that, right? And yeah, so this one we design it as alpha and beta left hand side. We call it as a terminal solid solution. Okay, that appear at the end of the phase diagram. Okay, and then another important thing is definition of the solvers, solidus as well as liquidus. This is more to the phase boundary. Okay, this one is a liquidus. This one, right, and this one is a solidus because on the solid, this one solid, and this one is a liquid, as well as this one two phase. Okay, this one liquid, this one is solvus. Okay, this one is solvus. Okay, so this is the phase boundary of liquid and pro-eutectic solid phase. Okay, what is pro-eutectic we will discuss later, as well as the this is a separating the two uh between solid and as well as liquid and solid, another solid. Okay, so this is the maximum solubility of the solid in the solid solution. Okay, you have to remember this one. Generally, how many percent we can determines. Okay, for A as well as B. Okay, this is the maximum. Okay, as for example at this temperature. Okay, actually for this eutectic also we have a 3 point. Okay, 3 point, we call it as eutectic point here. Okay, for the phase general phase diagram also they have three uh 3 point, right? The degree of freedom is equal to 0, right? Similarly, also this one is the degree of freedom is equal to 0. This one what we call is eutectic point. Okay, so yeah, so this one is a eutectic composition here at this point. Okay, so the cross between this line as well as this line. Okay, so freeze at the lower temperature than all other alloy conversion as well as eutectic temperature T and C is the lowest temperature at which the liquid phase can exit when cool slowly. That means from liquid to solid to here. So this is what we call as a eutectic point. Eutectic composition and eutectic temperature, we call it as eutectic point. Okay. Similarly, like general phase diagram, degree of freedom is equal to 0. So when liquid of eutectic composition is slowly cooled to eutectic temperature, okay, the single liquid phase transform into two solid phase. Okay, so it's clearly there when you cooling. Okay, this is liquid phase, and then 100% of solid solution of alpha and beta. So just cooling, and if you reverse the direction, okay, this is solidification. This one is liquefaction, so it's going to be 100% solid liquid. Okay. Okay. So this is what for the conversion or the reactions. Okay, from the liquid. Okay, to the solid solution of alpha and beta. Okay, we call it also as a eutectic reaction or invariant reaction. Okay, because it's occur at equilibrium condition at the specific temperature and alloy composition. Okay, so this reaction we cannot vary actually. Okay, according to the Gibbs rules, and this is a degree of freedom is equal to 0. This one, right? Okay, so just remember this one eutectic reaction or invariant reaction. Okay, so yeah, this is the what I already told you. Eutectic reaction is an invariant reaction because occur under equilibrium condition. And degree of freedom is equal to 0, definitely. Okay, at eutectic point, three phases are in equilibrium, so you have to remember liquid, alpha and beta. Okay, this one. So you can see here that liquid, alpha and beta. Okay, that point. Okay, any question about this definition? So similarly also we're gonna calculate the what is it, the chemical composition, the fraction, as well as uh what else? You have to sketch the microstructure development just similarly like general phase diagram to for 100% solid solidity. For phase eutectic also we're gonna do the similar thing. Okay, any questions for this one? Okay, so if no questions, let me move. Okay, to the example, some example of the binary eutectic alloy system for copper and argentum. Okay, so this is an example. For the copper and argentum, okay, the compositions are just atomic with atomic percents for the argentums. Okay, so here if you look at here that from left to the right. Okay. So 100% is argentum and right to the left is 100% of the copper. Okay. So this is the eutectic points. Okay. So characterized by the limited solid solubility of each terminal phase, alpha and beta. Yes, definitely. The most important feature of this system, the eutectic invariant reaction here. Okay. At 71.9% of argentum and 179 degrees C. So that means this is a eutectic temperature. And the composition, eutectic composition is 71.9. Okay. So this is the invariant reaction. Okay. Or eutectic point. At eutectic points, so if you look at here, alpha is 8% and beta is 91.2%. Okay. So How can we determine this one? And the liquid definitely 71.9 argentums. Okay, how can we determine 8% and 70 and 99.2%? So if you look at here, this is the eutectic point. Okay, right. And at 779. See, this is the end of the what is it? The line, right? So just draw this vertical line here and this vertical line here. Okay, so you can see here that alpha, right? Alpha is around 8% here. Oh, sorry. Yes, yes. Okay, this is alpha. See? So only 8% of argentum. Okay, is become solute for argentum. Okay, and this one is 19.1% of argentum, and solute is copper. The rest is for copper. Copper is solute. This one, copper as a host, the alpha. That's why alpha is 8% and beta is 91.2%. This is at the eutectic isotherm for the invariant or eutectic point. Okay, just draw the straight line. This is at 779 degrees C. Okay, so eutectic isotherm is the horizontal solidus line at TE here. Okay, this is TE. There is no liquid below TE. This one. Just below this one, 779 is no liquid. Okay. Okay. Clear? How to determine the composition at the eutectic point, 779 degrees C. Okay. So you can see here that three phases can coexist. Liquid alpha, solid alpha, solid beta, as well as the liquid. Okay. And this one, eutectic composition if is at 61.9 61.9 sternum. This one is a lead and sternum. Okay, at 180 degrees. So what you have to do? Yes, similarly, right? 61. Okay, just draw the straight line. Okay, 183. Yeah. Okay. So similarly, this one you draw the straight line. This one also you draw the straight line. So you can know the composition at the eutectic point. Okay, easy, right? So this one here, and this one is here, and this one is here. Okay, at eutectic point. Okay. So what we can say here that alpha phase is the lead rich solid solution. Okay, this one alpha phase. This one 100%, almost 100% plumbum or lead. And 180 degrees C, a maximum of 19.28% of sternum can be dissolved. So here, okay, only 19.2% can dissolve in argentum. Okay, this one 19.2%. How about phase beta phase? Okay, this is a sternum rich, yeah, for beta, and only 2.8% of plumbum. The rest, because 97.5% of the sternum that plumbum rich, only 2.58% of lead can dissolve in sternum. Okay, at eutectic. Okay, so when you slow cooling, okay, at 300 degrees C, okay, at 61.9 for the lead as well as sternum, we can see here that the microstructure development from the solid from the liquid to the solid, right? So this one we differentiate with the different color to differentiate between alpha and beta. Actually, alpha maybe we can define as what is it, as alpha, and red maybe we can define as a beta. Okay, so this one is at TE or here. Okay, liquid solidified by eutectic reaction into two solid alpha and as well as beta. Okay, and further cooling PE to room temperature, solid solubility of solute in alpha and beta phase decrease as indicated by Solbers or Solbers line. Okay, this one. Okay, so this is in terms of microstructure development, but we're going to discuss in detail later. Okay, don't worry. Okay, any question about this one? How to determine the composition at the eutectic point? Any question? So no question. Okay, just I guess no question. Maybe we can stop here. Okay, at the eutectic point, right? Just introduction about the phase eutectic. Okay, and next week we're gonna discuss further about how to calculate the phase diffraction. Okay, as well as what is the difference with the primary eutectic as well as a pro-eutectic. Okay, this one is how to draw the what is it, protetic alpha, protetic beta. Okay, the microstructure development. Okay, and then we can see what is the yeah, this one is microstructure development. This is from the, I think it's from the, I'm not sure, SEM or TM analysis. Okay, so okay, this is the analysis. Next week we can next week I don't think we have, is a semester break, right?
Yes, Doctor.
Yeah, okay, okay. So we're gonna discuss after the semester break. Is it okay?
Okay, Doctor.
Okay. Okay. Any more question? Just some introduction about the phase tactic before we go further details after the, okay, so far no, it's easy, right? Okay. If you have no questions, maybe later you can try this phase diagram. Okay. For the yeah, general phase diagram for 100% solid solubility. Okay. So if you now have questions, I think that's all for today, just for 1 hour. Actually, I have to attend some program around. Actually, already started the program. Any more question? Okay, that's good. No question. So is clearly my explanation is clear. Thank you very much, guys. So see you after the mid semester break. Okay.